Have you ever stopped to wonder what makes a lemon so sour, but then soap feels so slippery? Well, today we're going to crack the chemical code that governs our world by diving into the secret life of acids and bases.
Okay, let's kick things off with something you've definitely experienced. Picture it. You bite into a fresh, juicy lemon. You get that sharp, tingly, mouth-puckering sensation, right? We all know it. But what's actually happening in there, chemically, to create that taste?
Now let's do a complete 180. Think about washing your hands. That feeling of soap, it's slick, it's slippery, it's almost a little slimy. It's the total opposite of that lemon. So what gives?
Well, the answer to both those questions lies in the exact same place. It's not magic, it's pure chemistry. There is this invisible chemical code that defines all these substances, giving them their unique personalities. And today, we're going to crack it.
So, the key to understanding this code is a tool called the pH scale. The best way to think about it? It's like a chemical ruler. It lets us measure and make sense of this hidden world all around us.
Basically, the pH scale is just a ruler that goes from 0 to 14. The lower the number, the more acidic something is. And it's all based on one little thing, the concentration of hydrogen ions. The more hydrogen ions you've got floating around, the more acidic it is. It's that simple.
So you can think of this ruler as having three main territories. Anything with a pH from 0 up to 6, that's the acid zone. A perfect 7, right in the middle, that's the neutral zone. Think pure water. And then everything from 8 all the way up to 14, that's the base zone.
First stop on our tour, let's jump into the low end of the scale. Welcome to the acid zone, which is home to some of the most reactive and recognizable substances we deal with every day.
So what really makes an acid, well, an acid? What's its secret sauce? It's simple. When you put it in water, it just unleashes a flood of hydrogen ions. That's its whole deal. That's what makes an acid do what it does.
And trust me, acids are absolutely everywhere. I mean, our own stomachs produce this incredibly strong acid, hydrochloric acid with a pH around 1.2, just to digest our food. That lemon juice we talked about, pH of 2.2. Even the soda you might be drinking has carbonic acid.
So how do you spot an acid out in the wild? Well, two dead giveaways. First, if it tastes sour, odds are pretty good it's an acid. And if you're in a lab, a simple litmus test nails it. Acids always turn blue litmus paper red.
All right, we've explored one side of the map. Now let's travel all the way to the other end of our chemical ruler, up to the high numbers. This is the base zone, and it's pretty much the chemical opposite of the world we were just in.
You can think of bases as the anti-acids. They're the yin to the acid's yang. Instead of releasing hydrogen ions, they do the opposite. They either release hydroxide ions, or they go around gobbling up any free hydrogen ions they can find.
And just like acids, bases are super common. Baking soda, a pretty mild base, is probably sitting in your kitchen cabinet right now. That soapy water that gives us the slippery feeling? It's hanging out at a pH of 12. And really powerful cleaners, like lye, are extremely strong bases.
So here's the takeaway. Their properties are a mirror image of acids. Instead of sour, they're bitter. If you've ever accidentally gotten soap in your mouth, you know exactly what I'm talking about. And that classic slippery feeling, that's the telltale sign of a base.
So we've got these two opposing forces, kind of like the hero and the villain of our chemical story. But what actually happens when an acid and a base finally meet? Well, you get a dramatic chemical reaction called neutralization. So just to put it all side by side, acids give away hydrogen ions, taste sour, and live below a pH of 7. Bases accept those ions, taste bitter, and have a pH above 7. They are perfect chemical opposites.
And when you mix them, they basically cancel each other out. The hydrogen ions from the acid and the hydroxide ions from the base get together and form water. And whatever's left over combines to form a salt. Now, just so you know, in chemistry, a salt is any compound made from this kind of reaction, not just the stuff you put on your food.
And you've probably seen this in action without even realizing it. You get heartburn, right? That's because you have too much stomach acid. So you take an antacid, which is just a mild base, like milk of magnesia. That base goes in, neutralizes all that extra acid, turning it into harmless salt and water, and boom, you feel better. It's chemistry to the rescue.
And this is where it gets really interesting, because this isn't just about cool lab experiments. The balance of acids and bases is absolutely fundamentally crucial for all living things.
Seriously, this balance can be a matter of life and death.
Your blood has to stay in this unbelievably narrow pH window between 7.35 and 7.45. If it strays even a little, the vital enzymes that basically run your body's software, they change shape and just stop working. It's that critical. Even a small pH drop in your mouth starts to dissolve your tooth enamel. And on a huge scale, acid rain can decimate entire ecosystems.
Think about that number, 7.4, the average pH of our blood. It represents this constant, delicate, non-stop balancing act our bodies are performing every single second just to keep us alive. It's a testament to how life itself is built on maintaining this perfect chemical equilibrium.
Which really leaves us with a big final question, doesn't it? We've seen just how incredibly important this chemical balance is, from our own blood to the planet we live on. So what are the real consequences when our diets, our habits, or our industries start to tip that scale? That's definitely something worth thinking about.